Have you ever hit a wall on a math problem that seems just impossible? Well, in the world of engineering and science, the goal isn't always about finding the one perfect, exact answer. It's about getting an answer that's so incredibly close, it's practically just as good. And today, we're diving into a really clever shortcut that does exactly that. Okay, so take a look at this. Imagine you have to find the area under this weird, wiggly curve. You can see right away that a simple rectangle or a triangle just isn't going to cut it. This is a classic problem in calculus, right? Integration. So how on earth do you measure a shape that seems to break all the simple rules? Here's the thing. For a lot of these complex curves, finding the exact area isn't just hard. It's literally impossible. So what do? We change the goal. Instead of chasing that perfect number, we look for a really, really good approximation. An answer so precise you could build a bridge with it or design a computer chip. And that leads us to the big idea. If you can't measure the whole thing in one go, why not slice it up into smaller, more manageable pieces? And then, and this is the cool part, instead of using clunky, simple shapes for those slices, we're going to use something way more elegant. So let's compare two ways of doing this. On the left, you've got the basic approach. Just cram a bunch of rectangles under the curve. It kind of works, but you can see all those gaps and overlaps. It's a rough guess at best. But now, look at the right. That is a smarter fit. We're using a smooth curve that basically hugs the original line. It's obvious that's going to give us a much, much more accurate answer. So what is this magic smarter fit curve? It's something called a cubic polynomial. The easiest way to think about it is like a super flexible wire that you can bend and twist to perfectly match the shape of our original curve over a small distance. And that sophisticated little tool is the secret weapon we're talking about today. And that brings us to the tool itself. Let's meet the star of the show, Simpson's 3/8 rule. This is the actual mathematical formula that puts those clever cubic curves to work for us. So what is it? Put simply, Simpson's 3/8 rule is our recipe for this whole process. It's a formula that tells us exactly how to slice up our area, and then how to use the height of the curve at very specific points to build those perfect fit cubic curves and get a final super accurate area. All right. I know. That formula looks like a bit of a monster. But don't panic. We are not going to get lost in the weeds deriving it. Just think of it like a recipe. The important part isn't memorizing every little symbol. It's just knowing what the key ingredients do. So let's break this down real quick. H is just the width of each of those little slices we made. Easy enough. Y is the height of the curve at each of those slices. And those weird numbers, the 3s and the 2s, that's the secret sauce. It's a special weighting pattern that gives just the right amount of importance to each point, making sure a cubic curve sits perfectly. It's also why this rule has one very important catch. You have to use a number of slices that's a multiple of 3. Okay, enough theory. It's one thing to talk about it, but let's see this thing in action. All right, here's our mission. We need to find the area under the curve y equals x to the 4th, all the way from x equals -3 to x equals +3. And we're just going to follow these 4 simple steps. Figure out the task, slice up the area. We'll use 6 slices, which is a multiple of 3. Find the heights at each slice, and then just plug it all into the formula. So here's our data. We split the area into 6 equal slices, which gives us 7 points to measure. This table shows the height of the curve, our y value, at each of those points. So you can see when x is -3, the height is 81. When x is -2, the height is 16, and so on. Now, we've got our numbers. Let's feed them into the recipe. So we take all of those y values, we plug them into that big Simpson's 3/8 rule formula, we crunch the numbers, and what do we get? We get 99. A nice, clean, simple number. But that brings us to the most important question of all. So we have our answer, 99. But is it a good answer? I mean, how close did we really get to the true value? It's time for a little reality check. And here we go. This is where you really see the magic. On the left, there's our answer from Simpson's rule, 99. And on the right, that's the actual, true, exact value, 97.2. You don't even need the numbers. Just look at the bars. They are incredibly close. The difference, the error between our good enough answer and the perfect one is just 1.8. I mean, for a problem this complicated, to get that close with a pretty straightforward formula, that is absolutely amazing. This is what we're talking about. The good enough answer is more than good enough. So let's just zoom out for a second and think about the big picture here. What's the main takeaway? why do methods like Simpson's rule even matter out there in the real world? Well, here's the rundown. Simpson's 3/8 rule is a seriously powerful tool for figuring out the area under tricky curves. It works its magic by fitting these elegant cubic curves to the data, and the key thing to remember is that one constraint. Your number of slices has to be a multiple of 3. Why does it matter? Because in everything from engineering and physics to data science, the ability to get a hyper-accurate answer to an impossible problem is literally what lets us build and understand the world around us. And that kind of leaves us with one last big question to think about. We've seen just how powerful a good enough answer can be. So the real question is, in a world that always seems to be chasing perfection, when is an approximation not just a shortcut, but actually the most powerful tool you have?